In this video, I'm going to go over the solutions to questions 33 to 38 from section 5.3. So question 33 wants to know which of the following is equivalent to the bond enthalpy of the carbon-oxygen bond in carbon monoxide. So first of all, you have to realize that when we're talking about bond enthalpies, both reactants and products have to be in the gaseous state. So that means letter A is not an option and letter C is not an option because they both contain carbon as a solid over on the product side. So then the question is whether or not B or D is my best option. Well, in letter B and C both, carbon monoxide is the only reactant, so the triple bond there is going to be broken. But in letter B, no new bonds are formed, whereas in letter C, an OO double bond is formed, and even though it's only half the energy of that, that still is energy that's going to be subtracted from the CO bond enthalpy. So only B truly represents the bond enthalpy of the CO bond. In question number 34, they want you to use the bond enthalpies to calculate delta H for the reaction. So when I look at this, the H2C is letting me know that it's two hydrogens single bonded with the carbon double bonded and the H there. And then I've got the H2 single bonded to itself. And over here, I'm going to have the carbon single bonded between the two carbons, and then the three CH bonds. And remember, it's reactants minus products, but if I look at what I have here, I have 4 CH single bonds, plus I have a carbon-carbon double bond, plus I have an HH single bond. That's my product side, my reactant side. And from that, I have to subtract the value of 6 CH bonds and 1 carbon-carbon single bond. So really, when I look at my net here, I've got a net of 1 carbon-carbon double bond, or positive 612, plus the hydrogen-hydrogen single bond, which is 436. And then that's going to be minus 2 carbon-hydrogen single bonds, so 2 times the 413, plus the carbon-carbon single bond, which is 347. And when I punch in the numbers, I end up with negative 125 kilojoules. So an exothermic process. In number 35, I'm asked to use the bond enthalpies again to calculate delta H. So this time I have 2H2, so those are single bonds, and it's going to be 2 of them. And then I have O2, which is a double bond, and it's forming H2O, which is going to be a total of 4 HO bonds because there's 2 hydrogens in each water bonded to the oxygen. So I don't have any canceling out to do on the reactant and product side, but I can go ahead and plug in my values. I've got 2 times 436 plus 1 oxygen double bond at 498 minus the 4 times the OH bond at 464. And that's given me a net negative 486 kilojoules. Number 36 is actually very similar to number 34. It says the hydrogenation of the alkene double bond in unsaturated oils is an important reaction in margarine production. So unsaturated oils, they often break the double bond and add more hydrogen to it, and when there's all single bonds, that's what we call saturated molecules. So calculate the enthalpy change when 1 mole of C double bonded carbons is hydrogenated from the bond energy data shown below. So the simplest example I could have is if I had just 2 carbons double bonded and then there'd be 4 hydrogens as I've shown. I'd have to add 1 hydrogen molecule to break that bond, and I would end up with the 2 carbons single bonded surrounded by the 6 hydrogens. And again, this is the same equation we just used up in number 34. And my calculation is actually be slightly different because now they say the CH bond is only 412, whereas up in 34 they listed it at 413. But I would look at the same thing. I've got 4 CH bonds plus a double bond carbon plus the hydrogen single bonded minus the 6 CH bonds and the carbon-carbon single bond. So when I plug in, I can go ahead and reduce this, cancel out the 4CH on one side and leave 2CH on the other. So the carbon-carbon double bond is still listed at 612. The hydrogen single bond is 436. And then I'd have to subtract the sum of 2 times the CH bond, which is now for some reason only 412, and the carbon-carbon single bond at 347. And now my result is going to be negative 123 kilojoules per mole, or letter B on your choices. Number 37, you're asked to use the bond enthalpy data to calculate the enthalpy change of reaction between methane and fluorine. So C2H4, if I single bond the 2 carbons and put just the 4 hydrogen on, I realize that I'm short a bond for carbon, so that lets me know there's a double bond there. F2 is just going to single bond to itself since it already has 7 electrons. And then CH2F, CH2F, that's what's called a condensed structural formula. That's basically telling you how to draw it. Carbon, hydrogen, hydrogen, fluorine, bonded to the other carbon, hydrogen, hydrogen, fluorine. So when I look at what my net bonds are, I have 4 CH bonds, plus a carbon-carbon double bond, plus a fluorine-fluorine single bond. And on the other side, I have 4 CH bonds, a carbon-carbon single bond, and 2 carbon-fluorine bonds. So my 4 CHs cancel out. There's no need to include that in the calculation. So my carbon-carbon double bond is 612. The fluorine single bond is 158. Minus on the other side, my carbon-carbon single bond is 347. Plus my 2 carbon-fluorine bonds are 467. And so I come up with a net value of C, negative 511 kilojoules. So number 38 says use the bond enthalpies given in section 11 of the data booklet to estimate the enthalpy of combustion of ethanol and comment on the reliability of your result. So in 38, what you have to know is that ethanol is C2H3OH. And we haven't gotten to the organic stuff yet. We won't get to that till chapter 10. But if you look in your data booklet, you can find these formulas pretty readily. You won't have to memorize them. And then since it's combustion, it's going to be plus O2, gives you 2 CO2 and 2 H2O. So I've gone ahead and balanced it here. So what you have to really do is look at what your bonds are. So I've got carbon bonded to carbon with an OH, a hydrogen, and a hydrogen. Actually, I've got my H's wrong. This is going to be C2H5OH because this is a saturated compound. There's no double bond there. And then my O2 bond is going to be a double bond. And again, you'll just get more confident with these with practice. And my CO, I've got this messed up. I need room for 2 oxygen bonded on there. And that's going to be times 2. And then my H2O is also going to be times 2. So when I look at my net bonds, I've got 6CH plus a carbon-carbon single bond plus a carbon-oxygen plus an oxygen-hydrogen plus an oxygen-oxygen double bond. And that's going to be minus my product side, which is going to be 2 carbon-oxygen double bonds and 4 oxygen-hydrogen single bonds. Now I do have an oxygen-hydrogen single bond up here, so I can reduce that to 3, but that's all that cancels out. So then I just have to go look up my values and plug in here. And after looking at the values on the chart on page 11, figure 11, I came up with a net value of negative 1263 kilojoules. And I've gone ahead and written in the values that I looked up on page 11 if you're curious where I got my numbers from. So 6 times 414 plus 346 plus 358 plus 498 minus the sum of 2 times 804 plus 3 times 463. And again, I got a negative 1263 kilojoules.